For this video, we're going to take a closer look at mechanical advantage. When we use a machine, the reason we use it is because it helps us to do work. There's 4 ways that machines can help us to do work. One example is to transfer effort force from one place to another. The best example of transferring your effort force can be seen in a simple seesaw on a playground. A machine also helps us by multiplying our effort force. So if you think of a crowbar, it's used to maybe do a difficult task that we can't do with just our bare hands. A machine can help magnify the speed and the distance. For example, think about a baseball bat used in a swing. That ball is going to travel faster and farther when it's hit with the baseball bat than if we were just to simply hit it with our hands. A simple machine can also change the direction of the force. Okay, an example would be the pulley on the flagpole. So by pulling down on a rope, the flag is raised up in the air. Keep in mind that when we say the word machine, it's a device with which you can do work in a way that is easier or more effective. So they can make work easier by changing the amount of force that you put in, changing the distance over which you exert the force, or by changing the direction in which you exert your force. We'll take a closer look at all 3 of these things throughout our unit. Anytime that a machine is helping us to do work, it's creating some kind of a mechanical advantage. And a mechanical advantage is simply the number of times a machine multiplies your effort force. For example, if you push on the handle of a car jack with a force of 30 pounds and the jack lifts a 3,000-pound car, the jack has a mechanical advantage. If we think about what that mechanical advantage is, the jack multiplies your effort force by a factor of 100. So by putting in 30 pounds of force, I could lift a 3,000-pound car. Take another example. It's almost impossible to crack this walnut with our bare hands. So instead, we're going to use a nutcracker. Okay, the nutcracker increases the applied force. Take a moment and see if you can figure out why and what's taking place. When we talk about mechanical advantage, we're focused on a ratio. 1 is the magic number that those ratios are kind of compared to. If the mechanical advantage is greater than 1, that means it took less effort force to overcome any kind of resistance force that you're lifting. In doing so, though, we have a greater effort distance to overcome that resistance force. Now, you can also have a mechanical advantage less than 1. If the mechanical advantage is less than 1, that means proportionally there was a greater effort force required to overcome any resistance force. If you have a greater force, that means you're going to have proportionally less effort distance required to overcome the resistance force. And there are some simple machines where even though we have a mechanical advantage less than 1, we need that smaller effort distance to do the task. It's important to note that a mechanical advantage can never be less than or equal to 0. We're always talking about it in terms of a ratio, so it's going to be a number greater than 1 or it's going to be a number less than 1. Mechanical advantage can actually be classified in 2 different ways. One is the ideal mechanical advantage, and the other one is the actual mechanical advantage. The difference between these is basically how it was designed versus how it actually functions. If I'm focused on an ideal mechanical advantage, this is the number of times a machine is designed to multiply your effort force. The ideal mechanical advantage is based purely on the measurements of the machine, and it doesn't take into account any frictional forces that might be present. The actual mechanical advantage, on the other hand, is the number of times the machine actually multiplies your force. And it's a ratio of the resistance force that you're lifting over the effort force that you've put in. The actual mechanical advantage is always going to include the effects of friction. So in other words, it's a real situation, how the machine is actually functioning. Your ideal mechanical advantage is always going to be greater than your actual mechanical advantage due to those effects of friction. When we focus on the actual mechanical advantage, that mechanical advantage is what the machine provides in a real situation. You can only determine the actual mechanical advantage by physically measuring the true input and output forces. You can't determine it in advance because those actual values depend on the efficiency of the machine. Okay, so let's take a look at the math involved in calculating an ideal mechanical advantage. Again, when we talk about an ideal mechanical advantage, that's your theory-based calculation. So we're not taking into account any friction loss, and it's based on how it was built. So we're looking at the distance traveled by effort and the resistance force. If you look at the equation, IMA simply stands for your ideal mechanical advantage, and notice how we have distance of the effort divided by distance of the load or the resistance force. Since we're talking about distance, we could be talking about feet divided by feet, or maybe meters divided by meters. Either way, we're talking about two different distance units, so those cancel out, and our ideal mechanical advantage is a unitless number. Take, for example, the idea of lifting a box straight up versus using an incline to push it up the incline. If this ramp gives us a mechanical advantage of 4-to-1, what it's telling us is that the effort force magnitude is 4 times less than the magnitude of the resistance force. Okay? In other words, it's going to take a lot less effort to push the box up the ramp than to pull it straight up. If we focus on the distances traveled by the forces, the effort force has to go 4 times the distance than the resistance force. If I compare lifting a box straight up to pushing it up the ramp, it's taken me 4 times less effort to push it up the ramp. So my ideal mechanical advantage, where that 4 times greater distance comes from, is our ideal mechanical advantage that you see in the bottom left. So the distance of my effort, okay, so the effort would be directed along the ramp, okay, that has to be 4 feet for every 1 foot I lift it up. I can use this ideal mechanical advantage equation in another way. Okay, let's say that we know that this box, okay, weighs 100 pounds. I want to figure out how much effort do I actually have to put in. What I can do is set this ideal mechanical advantage equal to our ideal forces, and I can figure out the force of the load over the force of the effort. If my ideal mechanical advantage was 4 and the load is 100, ideally speaking, my effort should only be 25 pounds. So to get that box pushed up the ramp, I have to apply 25 pounds of effort force to lift it upwards. Okay. This right here is known as our ideal effort force. Now, our actual mechanical advantage is an inquiry-based calculation. So in other words, we're having to take measurements of our actual machine in order to figure out what kind of friction losses happened along the way. Our actual mechanical advantage can only be found by taking the force of the load over the force of the effort. Okay, so how much load the actual load I lifted over my actual effort. These two numbers, again, the units are going to cancel, so I'm left with a unitless number. So an actual mechanical advantage, again, it's an inquiry based, so it's based on how it's actually built, and you physically have to take numbers of the machine to see how well it's performing. Okay, so there's your basic ideas of ideal mechanical advantage and actual mechanical advantage. Either way, it's just a ratio of how easy it is to do work based on that simple machine.